This is video 5 from the GCSE Physics video series. This one is about domestic electricity, appliances, that sort of thing. Couldn't think of a better name for the video, but that'll do. Right, so this is lesson 26, starting with alternating current. So we're going to define what alternating current is. Direct current, which is sort of the opposite to alternating current, that's one where the charge is flowing in one particular direction. It doesn't have to flow continuously, but it always flows in one particular direction. This is the sort of current that you get from a battery, for example. Alternating current is one where the charge reverses direction as it flows. Repeatedly reverses direction, forwards and backwards and forwards and backwards. And in that case, we say that the current is alternating. It is important to note that direct current does not mean the current is always the same. It's just that it's in one direction. I made that bold. It's very important. So when we talk about direct current, we've got a positive terminal and a negative terminal. Fine. Of a battery, you've got a positive side and a negative side. No problem. With a alternating supply, we don't have a positive and a negative side. We have one terminal which is fixed at 0 volts potential, and we call that the neutral terminal, the neutral connector, into which you attach the neutral wire. And then we have the other one where the potential goes from being positive to negative to positive to negative. And we call that the live connector, the live terminal. And the wire that connects to it we call the live wire. And in our domestic, on our domestic mains supply in the United Kingdom, our live wire goes from being positive 325 volts to negative 325 volts. And then back to positive again, and so on and so on and so on. And the whole cycle from positive to negative back to positive takes about 0.02 seconds, giving us a frequency of 50 hertz. That is to say that the positive to positive happens 50 times per second. We'll talk about the relationship between time period and frequency in a later video about waves. So we can't talk about having a positive terminal and a negative terminal, but we do have a neutral terminal and a live terminal. And the live one is the one where the potential difference is varying. So sometimes the live one is negative and the neutral one is 0, so the current flows in one direction. And sometimes the live is positive, the neutral is 0, so the current flows in the other direction. And you always have to have a circuit completing you have to have a complete circuit connecting the live to the neutral for your from your supply into your appliance and back to your supply. Okay, so we've got this other word here which comes up called polarity. Polarity talks about which terminal is more positive, which terminal is more negative. So effectively what we could say is for a DC supply, the polarity never changes. But for an alternating current supply, the polarity keeps reversing. Which side is more positive and keeps changing. 0 is more positive than negative 325, but positive 325 is more positive than 0. So the polarity of our supply keeps switching. There's a type of average which we don't talk about much at GCSE level. It's called a root mean squared, but don't worry about that. We do that at A level. There's a kind of average. If you just calculated the mean of 325 and negative 325 volts, you'll get 0 volts, which isn't very useful. But there's a type of average that takes into account the fact that whether the potential is positive or negative on the live, it's still going to be pushing charge around. It's still going to cause a current. There's still going to be work being done by charges that are moving through components. And that type of average, it's called a root mean squared, don't worry about that, but that type of average of these of this supply gives you 230 volts. Now in the UK it's actually closer to 240, In certain parts of Europe, it's actually closer to 220 volts, but on average, it's around 230 volts. That's what legally, I think, we say that our main supply is in the UK. 230 volts. Then we're going to talk about some other key things. The national grid. I've talked about this in a previous video. This is the cable. Whoops. Go back to the right video. This is the cables and transformers through which the charge flows. Does not include the pylons, even though they are owned by the company National Grid. They're not part of the national grid. National Grid uses alternating current. There's a sort of diagram of what the national grid does on the right, which I'll talk about in just a second. In fact, I'll talk about that now. So on the one side of the national grid, you've got these private companies that own these power plants. There are nuclear power plants, coal power plants, they're in the minority. There's hydroelectric plants, we talked about those in a previous video as well. Yeah, they're all on one side of the national grid. On the other side of the national grid, you've got industry. So that's factories that need to use power to make stuff. You've got industrial customers. You've also got domestic customers, so homes down here. And there's probably some other things in there as well. There's sort of commercial properties that aren't really included on this picture. Much different to homes, to be honest with you. Just need to keep the lights on and the computers turned on and things like that. But anyway, so that's the two sides of the national grid. The supplier side, owned by private companies, and the consumer side, owned by private companies, or in the case of industry, or people, in the case of, domestic supplies. But also you've got hospitals in there. They're owned by trusts at the moment. Hopefully it will stay that way. The NHS owns most of the hospitals. There are some private hospitals, schools. Some of those are private. Some of those are owned by trusts. Are trusts publicly owned or privately owned? I'm not going into that. So you've got a lot of going on. In between the sort of suppliers and the consumers, you've got the national grid. The national grid consists of transformers and cables. So let's talk about what transformers are. On this diagram, they're represented by these interlocked circles. What transformers do is they change the potential difference. Or I should say the root mean squared, the average potential difference. There are two types of transformers. There are what we call step-up transformers, which increase potential difference by reducing the root mean squared, the average current. And then there are step-down transformers where they reduce the average potential difference by increasing the average current. Now, why we might need these, we can talk about a little bit later, but I will mention it now briefly. The power supplies are generating, in this case you can see, between 600 and 1,700 million watts. So that's, more than around about 1,000 million joules of energy, so 1 billion joules of energy per second being spat out of this nuclear power plant. And that is what it is. Now, that then is going to be transmitted to our homes via wires. As current passes through the wires, it has a heating effect, and the wires will warm up. That's why birds like sitting on electrical cables, because it's warm and it warms their feet up. Now the problem is, if I am warming up the cable because there's a current passing through it, then energy is being dissipated by that cable, by that transmission cable. So by the time I am getting the current to pass through my home to extract energy from to get energy transferred into my home, by the time I've got that happening, there's less energy I can get out of this system, out of the national grid, because I've wasted energy warming up the cables in between. Now we can reduce that effect by reducing the current that passes through the cables. Remember, current is what transfers the energy. So if I have less current, there's less energy being transferred in the cable. So if I increase the potential difference on average, I reduce the current on average while still delivering the same amount of power. There's an equation for that, which we'll look at in the next lesson, which is part of this video. So we increase the potential difference from about, what is it going to be, about 25,000, oh, it's here, at 25,000 volts, what we generate the electricity at. We increase it to around about 270,000 volts to transmit, and sometimes it could be higher than that, could be as high as 400,000 volts if we've got transmission over an even longer cable from one side of the country to another. We step up the potential difference. Now that's nearly 10 times higher potential, it's more than 10 times higher potential difference. So it's less than 10% of the current, which actually reduces the wasted power by 1% for reasons we'll talk about in a later video. So then we transmit at that very high potential a difference on average, very low current, and then the consumers come along and they want it. Now, if you just stepped from 270,000 volts down to 230 volts, let's just go straight to the customer, to me, to the home, the transformer would be incredibly wasteful. It would be a huge machine and it would not be very efficient. You want to go down in stages. It's more efficient that way. There's less waste energy that way. Transformers are very interesting things, and we'll look at those in a later video, much later video, the penultimate video about electromagnetism. But the equation we use for transformers doesn't really work in real systems unless you're very careful with it. It doesn't really work. You'll see. So we've got our potential difference increase. So we've got lower current. We get to the home, we need to do the opposite because we need current in order to transfer energy into the appliances, into the energy stores of the appliances to make them do what they're supposed to do. In the case of my home, that's probably lighting, heating. In the case of factories, that's probably mechanical parts that are moving, conveyor belts and drills and I don't know what. So we have to step down our potential difference average in order to increase our average current. So you'll find there are things called substations, which are step-down transformers. But in most areas where there's lots of houses, you'll have a few substations. If there's ever a power cut, one of these substations might have tripped out and it'll cut out a road or two, but the rest of the town will be fine. Then there are larger substations which step down from a high, let's say 110,000 as it shows here, down to 50,000 volts. And then there are other substations that step from the very high, 270,000 volts, down to 110,000 volts, and so on. You can see these. If you drive around the motorways, every now and then you'll see something. It looks huge, like a compound full of these big grey boxes with lots and lots and lots of wires connecting them. And those are our big substations, our huge transformers. And then within your home, you've got transformers in your consumer box, but then also you've got these sorts of things. Oh, I've just pulled my amplifier over. You've got these sorts of things. I don't know if you can see it. This little black box here. That is a transformer. That is transforming 230 volts down to 12 volts. Might be lower than that for my little amplifier to work. So we've got transformers all over the place. On the national grid, we also have our renewables. Now, they don't need... You don't really want to take energy from them and deliver it to a home via this huge trunk system here because there's very little energy being generated anyway, so it would just be tremendously wasteful. So we tend to have those connected more closely to the grids that the closer grids, the smaller grids, the neighborhood grids, the distribution grids, the city network, that sort of thing. So it's less wasteful. Some homes even have solar panels, photovoltaic panels on their roof, and then they can feed that back into the local grid if needed. I don't know many homes that have wind farms attached to them. So that's the national grid, and that's alternating current and some key terminology. It's important to be using that correct terminology. So let's move on to lesson 27, cables and plugs. So remember I said that we have a neutral connection and a live connection rather than a positive and a negative. So on a plug, on a standard UK 3-pin plug, here it is. On a standard UK 3-pin plug, we're looking from the back of the plug in this picture that you can see here. But on a standard UK 3-pin plug, you've got a neutral connection, you've got a live connection, and you've got an earth connection. As a matter of fact, I think this plug diagram is incorrect. I've got a horrible feeling this plug diagram is incorrect. Let's just have a little think. Fuse, well, it's going to be on that side there. Oh, no, it is correct. It is correct. I've just got this thing here, which is written back to front, which might help, it might not. Yeah, this little piece of card that's attached to it, which has live written on the right-hand side. If you place the card on the back of the plug, that's in the right place. If you place the card on the front of the plug, where you find the piece of card, it's actually labelled in the wrong place, because that implies that that is the live pin there, but actually it's that's the live pin there, which is what is shown on the diagram here. So just be careful. You've got these little pieces of card that tell you how to cut your wires when you're rewiring a plug. Just be careful how you interpret them, because that one there is back to front as you look at it. Very naughty. But if you look at the back of the plug, what's here is correct. You've got your live pin, which is roughly where my cursor is hovering here. And you've got your neutral pin, which is roughly here. And you've got your earth pin at the top. I haven't even mentioned the earth pin yet, but we'll come to that in a second. So the live pin in your connecting into your main supply, that has a potential going from 325 volts down to negative 325 volts. To make it so you've got a potential difference, you have to have something on the other side of that circuit, which is at a different potential. Let's have that at 0 volts, smack bang between the 325 and the negative 325, and that's on the left. And so these two wires, the blue wire and the brown wire, will connect to our appliance, to our washing machine or our toaster or whatever. And when this live pin, the brown one, the brown wire, the live pin, is connected to, is positive 325, then the current is going to flow, the charge is going to flow down the red one into the appliance and back out through the blue one. When this pin, the live pin, is negative 325, then the charge is going to flow the other way. By charge, of course, I'm talking about this effective positive charge. Yes, the electrons are flowing the other way. We talked about that in a previous video. Whenever I say current or flow of charge, I'm talking about effective flow of positive charge. We haven't mentioned what the live pin does yet, but the live pin is also the earth pin, sorry. But the earth pin is also connected to 0 volts. But this is a very local 0 volts. It's in your house. There'll be a big metal stake going into the ground, and that is what that earth pin is connected to. Now, some appliances don't even have an earth connection. My mobile phone charger, for example, doesn't have an earth connection. It has a plastic pin. And the pin does a few things, actually. You'll notice that the earth pin is slightly longer than the other pins. That's not an accident. The earth pin at the top is slightly longer because as you push that into the hole, it opens little shutters for the neutral and the live pin to go in. That's a feature of UK plugs that is an added feature for safety. So even if you don't have an earth on your appliance, an earth connection in your appliance, you still need a plastic earth pin just to open up the power supply, the socket for the plug to go into, for the live and the neutral pins to go into. So the color coding here, this is the way it has been since the 1970s. Before the 1970s, or during the 1970s, they switched. I can't remember the exact date. They switched to this color scheme. It used to be black was neutral, red was live, and green was earth. However, people with red-green color blindness found that difficult. It's not that uncommon, red-green color blindness. So if you accidentally connect these the wrong way round, then your appliance becomes absolutely lethal. I'll explain why now. In your appliance, if there's a metal case to it, a metal box, or any exposed metal on the outside, then you must have that metal connected via an earth wire directly to the earth in your house, the stake that goes into the ground. Now, why is that? Because if something goes wrong in the appliance, if there's a fault, and within the appliance something comes loose and a live wire accidentally disconnects and touches the inside of the metal case of your appliance, well, what's going to happen then is the case itself will have a potential going from 325 to negative 325 to 325. Your case will be live. So if you touch that case, then you complete the circuit. The chances are the resistance that you have is less than the resistance of the appliance, or might even be around about the same. It doesn't matter. There will be a considerable current passing through you, which will transfer energy to you, which will cook you. And that would be very painful and could lead to your death. If you connect these two wires the wrong way round, then your case, even if the appliance is in normal operation and working perfectly fine, I mean, it wouldn't operate, you'd plug it in, nothing would happen, you'd scratch your head, you'd touch the case, and then you'd get the shock. Hopefully just a small shock, not a full electrocution, but it could happen. So you've got to make sure that you're using these wired in a plug the right way around. Now, I'm 40, I'm in my 40s now. I cannot tell you how many times I have had to rewire plugs. It's just a skill that, as an adult, you need to be able to do. There's lots of reasons for that. I mean, obviously, I wired up this hut that I'm in now, but also I was cutting the grass a couple of months ago and accidentally cut the wire off my lawnmower. It happens to the best of us, and I cursed and swore at myself, and then I rewired it up again, because this is the sort of thing that, as an adult, you need to be able to do. Or you could pay someone an extortionate amount of money. I saw a Facebook post on some community Facebook page where someone was asking for a handyman to do some wiring, a plug up, and people were saying, look, either electricians were saying, look, just do it yourself. Do it yourself, because if I do it, I have to charge you, and it was like £200-300 because you've got the call out fee straight away, and that's at least £100 or £150 for an electrician. Honestly, if you want a lot of money, become an electrician, make a fortune. So they were saying, look, just honestly, go down to local shop somewhere, a little hardware shop, buy yourself a plug for 50p and wire it yourself. Just make sure that it's safe. Oh yeah, but I don't want to get sued, so don't you do it. Don't you do it. Make sure you pay a qualified electrician to do it so that you don't sue me when you get it wrong. Legally covered. So that's what the Earth does. The Earth is a very low resistance path directly to the ground, which bypasses all of the rest of the appliance so that the case is always going to be connected to the Earth. So if the live wire accidentally touches the case, it's still stuck at 0 volts. Now that will mean the current will become very, very high because there's very little resistance in your component. And remember, V equals IR. So for V going up to 325 volts, averaging 230 volts, and an R of almost nothing, the I is going to be really, really high with V equals IR. That's the way equations work. So what do we do to make sure that we're not just going to melt all the wires in our appliance? Or even worse, melt the wires behind the walls of our house, causing a fire? Well, to make sure that doesn't happen, we have a fuse. We'll talk more about the role of fuses in the next lesson, which is part of this video. But that's where the fuse sits. I'm not going to talk too much about the fuse at the moment. Now, you do need to label these parts. I don't know if these are correct. Let's have a look. 1, cable grip, yes. 2, neutral connector, yes. 3, earth connector, yes. 4, live connector, yes. 5, fuse. Yes, that looks like it's correct. This is what a ring looks like, a ring main. So all these plug sockets are connected in parallel with each other. you've got to have big, thick cables where you're going to have high currents. And because you're wiring these in parallel, if I connect a toaster to every single toaster is around 1,000 to 2,000 watts, so drawing nearly 13 amps. If I have 13 amps passing through this one and 13 amps passing through this, that's 26 amps. And if I've got 13 amps passing through, that's 39 amps. And 13 amps passing through, that's 52 amps. And then 63 amps that's passing through this cable. So you can see if I add a whole bunch of toasters on my ring main, I'm very, very quickly going to end up with 60, 70, 80 amps trying to flow through. Now these here are probably not rated at 60 amps. These cables will be rated at maybe 20 amps or something. So there'll be a consumer unit which has, it's not a fuse, it's like a breaker, an RCD, residual current device. We'll talk about how the RCDs work later, but it's basically a little switch. They don't tend to use fuses in the consumer unit anymore, this consumer box. What happens if too much current is being pulled through a ring main, a little switch goes off, and it cuts all the current to that. And that's to prevent the wires getting too hot and melting and causing a fire behind the walls of your home. That's what it's for. So if you ever find that something keeps tripping off in your consumer unit, there's two reasons. Either one, you're overloading a ring main, check what's on it, unplug everything, and start plugging things in one by one. Second reason is one of those appliances is malfunctioning and trying to draw far too much current, and it's not properly tripping off the fuse in it, so it might have the wrong fuse in it. And things like that. So the things you should check. If something keeps tripping off, don't just trip it back on again and again and again, because there's a fault somewhere. You're doing something wrong. Right, so there we go. The sockets are connected in parallel. You can see what's going on there. If you want to add a spur off this, there are legal requirements is the wrong word. You've got to follow the law. You can't. There's a certain amount you can add to a ring main, and then beyond that, you've got to set up a new ring main to your consumer unit. I don't know what that legal requirements are. You can go and look up the law about this sort of thing, or become an electrician and become a millionaire, I can't get my words out. I'm so excited. Earn a fortune. Become an electrician and do it for everyone else. One of the things you have to know is the law and keep up to date with it. Right, so human body 0 volts. Potential difference between live and human would become 230 volts on average. If you touch the live, you've got 230 volts potential difference between you at 0 volts and the live, which means that you're going to have a current passing through you and you're going to get cooked. What else do I need to talk about on here? Earth wire connected. In the case of a short circuit, oh yes, that's the technical word, when you're bypassing the appliance with very little resistance, we call that a short circuit. It happens if a fault develops. I've talked about that. When there's a short circuit, the fuse can melt if the current gets very high. We'll talk about that in the next video, but that is what happens. The fuse is a sacrificial component designed to, the wire inside the fuse will melt, which will did it again. The wire inside the fuse will melt, which will cut the circuit off so that the appliance becomes safe. It cuts it off right here at the live, so no current can flow in at all. The whole appliance becomes neutral. So we've talked about what happens. It says the fuse melts. It's the wire inside the fuse that melts. I'm not very happy with this wording, really. There's a note here about when you don't need an earth connection. And that's when the appliance itself is what we call double insulated. You'll be able to tell because somewhere on the appliance or on the plug, on the adapter, there'll be a symbol that is a small square, inside a bigger square. That just indicates double insulated appliances, which means that there isn't any exposed metalwork that you could touch that would cause you to have an electric shock. So there's no reason to have an earth connection. And there's a little bit down here about materials that we use. Plug pins made of brass. Yeah, these are brass. I've seen stainless steel used as well for plug pins. Or aluminium. I'm not a material scientist. Something non-corrosive though. Cable wire made of thin copper strands. The reason we use thin copper strands is because you can flex them more. But if you flex a cable too much, it will eventually break. So things like this. My ukulele here, it's my electric ukulele. The amplifier lead, it flexes a bit. But if you flex it too much, it's going to ruin the quality of the sound because all the little copper strands inside there are going to get damaged, and that would be bad. Cable insulation, a flexible plastic, plugs, a rigid plastic. By plastic, we're talking about some sort of polymer, polycarbonate, I don't know. I'm not a material scientist. Let's move on to lesson 28. These are fuses. Okay, and you can see some of them have the rating written on them, 3 amp, 5 amp, 13 amp. Those are the 3 fuse ratings that you need to learn. There are others. You can get 7 amp fuses, 10 amp fuses, 1 amp fuses. You can get them. These are all the same size, physical size, which can be a bit dangerous. You can see there are other fuses here. These are a different size to these. These you can see the wire, so you can easily tell whether the fuse is, what we say, blown. Okay, sacrificed itself for the good of the component of the appliance. You can see that because this wire can be visibly seen, whereas these, which have a ceramic casing, not a glass casing, you can't see it. These are the sorts of fuses you find in automobiles, cars, motorcycles, buses, and they've got the thin wire here, and you can see if that thin wire has melted to see if the fuse has, colloquially we say, blown. So there are different types of fuses, but 3, 5 and 13 you have to learn. If you have an appliance that is supposed to draw 4 amps of current in normal operation, then you would use a 5 amp fuse. If you use a 3 amp fuse, then in normal operation the fuse will keep melting. The fuse wire will keep melting. Use a 5 amp fuse and the appliance is normally drawing 4 amps, no problem. But if an appliance is designed to draw 4 amps, then the wires in the appliance will probably only be rated at 5.5, 6 amps, something like that. They wouldn't go much beyond that because it's a waste of money on the appliance. Take a desk lamp. A desk lamp is going to draw less than an amp. So they're probably going to put wires in it as thin as they can rather than wasting money on big, thick pieces of copper inside that desk lamp. It's going to be drawing less than an amp. So a desk lamp will have a 3 amp fuse in the plug, and the wires might be rated at 3.5, 4 amps. Be careful when you buy things online because they might cut corners and have even thinner wires then. Because under normal operation, the appliance isn't going to draw an amp, so stick a 2 amp wire in it, is what those cheap, dodgy companies say. The problem is if a fault develops. Now, if a fault develops, your appliance may start trying to draw 20 amps or something. If you are using a 13 amp fuse in an appliance that's supposed to draw 4 amps, but that appliance is malfunctioning, so it's now drawing 20 amps, then your 13 amp fuse will melt. But let's say the appliance is malfunctioning and it's drawing 12 amps. Okay, it's a 4 amp appliance. It's got a 5 amp fuse in it. So the wires in the appliance will only be rated at about 5.5, 6 amps before those wires start melting. Now, usually the 5 amp fuse would melt first, protecting the appliance so it doesn't catch fire. But you've gone ahead and stuck a 13 amp fuse in it. And now the appliance is malfunctioning and drawing 12 amps. The fuse won't melt, but the other wires in the appliance will, and they can catch fire. A very common cause of house fires is people using the wrong fuses or connecting too many appliances to a ring main and not having a properly checked, a properly serviced consumer box so it's not tripping off. And that's a really common way that fires happen. So when I wired up this hut, I've got an RCD, which I check regularly, between my hut and my house. So that if this tries to draw more than 13 amps, the entire building here, it will cut the power off. Just to make sure that I'm not going to cause a house fire while I'm in here recording videos. This is the circuit symbol for a fuse. We write the rating above it. And some reminders. Power is rate of energy transfer. We did that in an earlier video. Electric power is potential difference multiplied by current. Can't remember if we did that in a previous video, but let's just get a pen out so we can do a quick derivation of this. If potential difference is energy transferred divided by the amount of charge that is transferred, and current is the amount of charge that's transferred divided by how long it takes to transfer it, then if I multiply those two together, I'm going to have E divided by Q times Q divided by T. And you can see that the Q's will cancel. Change it to red ink. The Q's will cancel and you're left with E divided by T, which is power. So power is potential difference power is potential difference multiplied by current. So this is electric power. Now this equation down the bottom relates to what we talked about with the national grid. This equation down the bottom here. If power is equal to current multiplied by potential difference, I've just written them in a different order, and potential difference is equal to current multiplied by resistance, which is a rearrangement of the definition of resistance from an earlier video, then if I substitute that V into here, I've got power equals I, and instead of V, it's I times R. And I times I is also known as I squared. So that's how we end up with this equation at the bottom here. Okay? Power equals current squared times resistance. There is another equation, V squared over R, but we don't need to do that. Really, that's not going to come up in your GCSE. But what that tells us is if I half, for a particular resistance wire, say the national grid, the cables, the transmission cables, if I half the current, then I get half squared, so that's a quarter, half times a half is a quarter of the power, the energy transferred by that current through that wire. So I'm not talking about the transference of energy from the power supply to the home. I'm talking about the transfer of energy from one store to another, so into the thermal energy store of the wires, heating the wires so that that energy cannot be delivered to the home. So that's why we have to massively increase the potential difference. If we make the potential difference 10 times as much on the national grid, for the same amount of energy being delivered from the power station to the home, if the potential difference is 10 times as much, the current has to be 1/10 as much, and 1/10 of the current, 1/10 times 1/10 is 1/100th, or 1%. So we get 1% of the power wasted in the cables that would have been wasted in the cables if we had the original potential difference. So, if I have 250,000, let's say 25,000 volts at a certain current, if I increase that to 250,000 volts, the current is now going to be 10% of what it was, which means I have 1% of the wasted power, which means I'm delivering 99% of the energy, which is not bad in terms of efficiencies. So the skill we need here is understanding these equations, rearranging them, using them, but also knowing how to pick which fuse. Find the current that the appliance is rated to operate at in normal operation, and then find the fuse value that is the next one up. So 4 amp appliance, use a 5 amp fuse. 5 amp appliance, use a 13 amp fuse. 1 amp appliance, use a 3 amp fuse. 2 amp appliance, use a 3 amp fuse. 3 amp appliance, use a 5 amp fuse. So that is how that works. Let's move on to lesson 29. And I mentioned in a previous video that I will turn the Drude model on its side so you get a better feel for this. This is how currents transfer energy. We've kind of talked about this in a previous video, but here I've got my power supply. This bottom side here is positive, this top bar here is negative. This is a DC supply, but the same principle operates if it's an AC supply and we keep switching the polarity. Same principle operates. The electrons right now are attracted down towards the positive side, repelled by the negative side. That's the way I'm going to talk about it. Come at me in the comments. So these charges are in an electric field and they are falling, is the way I like to describe it, from one electric potential to another. And as they fall, they bounce off these. You can see quite clearly how they bounce off these ions. Every time they bounce off an ion, they transfer energy into the ion, making the ion shake more, increasing the kinetic energy of that ion on average, which increases the thermal energy store of the component, whatever this lump of metal is. So definition of potential difference, here it is. Got to memorize it. Potential difference in electric potential between 2 points is the potential difference. That's the difference in potential. Fine. And we talked about potential just being a measure of where you are in a field. It's the best way I'm going to use to describe it at the moment. Charge gains kinetic energy as it flows through here. So now we're looking at the really close up under a really good microscope to see what's happening. So the kinetic energy of the charges increases because it's moving from one potential to another one. Collisions transfer energy into the thermal energy stores of the ions. Fine, fine, fine. So these are the two equations we use to derive the equation for electrical power there. So that's a short little lesson. We don't need a lot more than that. It's just, do you have a feel for how circuits and energy works? And I think you do at this stage. So now moving on to lesson 30, the last lesson of this video, the last lesson of the electricity topic. So if you look at appliances, here's me holding an iron, which I haven't used in, I don't know, 6 years or something. I don't bother ironing my shirts anymore. Who am I trying to impress? So if you look on the sticker, I might have to zoom right in. Can I zoom in? No. Can I zoom in with this? Oh, I can. Look at that. If you look at the sticker, to see my face. If you look at the sticker, you can see down here it says 220 to 240 volts. That means you can use it in Europe, in the UK. Frequency 50 hertz, fine. And then 1,800 to 2,200 watts. So it's around about 2,000 watts that this iron is going to be transferring. 2,000 joules per second. So what does that mean? 2,000 joules, zoomed out too far. What does that mean? 2,000 joules per second. Well, well, I don't know what else to tell you. That's what it means. It's how much energy it transfers into the appliance because a current passes through it. This one here is a toaster, and you'll notice the toaster is much higher. To 2,550, so 2,550 to 3,000 watts, much higher. Frequency 50 hertz. It says 50 to 60 hertz because this can be used anywhere where there might be 60 hertz supply, but around 230 volts. I'm not sure where that might be. Maybe Brazil or something. I'm sure you can look it up. Some people will be fascinated by that. This is my electric toothbrush. Right here, or my old electric toothbrush. I've got a new one now. But there we go. This is drawing a whopping 1.2 watts in normal operation while it's charging. That's just the charging base there. 1.2 watts. That is a point. I know it's a comma, but remember that in almost all of the world, the comma is used as the radix point. That is the decimal point in decimal number of counting systems. So yeah, the comma is used as a decimal point, and the dot, the full stop, is used as a thousands separator in most of the world. So only in the United Kingdom, the United States of America, even I think Canada, but there are parts of Canada where it might be different. But yeah, in the USA, in the UK, they use a dot for the decimal point. But that's actually quite rare. That's not the norm. So very, very low power used by that appliance. What does that mean? That means it's going to be drawing very little current. Because if my appliance is drawing, let's say, 2,000 watts, 2,000 watts, where is it? Over here, 2,000 watts at 230 volts. Let's pull my calculator out and work out what current that's going to be. pulls out his calculator. 2000 divided by, what did I say it was? 230 volts, 8.7 amps. So I'm going to have to use a 13 amp fuse on that iron because it's drawing nearly 9 amps. But if I were to look at my electric toothbrush, 1.2 watts divided by 230 volts, 0.0052 amperes. Very, very low current indeed. So I'd stick a 3 amp fuse on that and be happy for it. Very, very low current passing through that electric toothbrush charger indeed. It's also double insulated, so it doesn't need an earth wire. That's the double insulated symbol there, the small square inside the big square. An IP67 refers to how watertight and dust tight it is, but I can't. Zoomed out too far. I can't remember what those different symbols mean. So you can work out by reading the label what fuse the appliance will need. You just use this equation, rearrange it to make I the subject, type in the power it's normally operating with, divided by the potential difference for the mains, 230 volts, and that will tell you the current you can expect to be drawn by that appliance. Efficiency, we've talked about this last time. You might find efficiency useful. Just a reminder, an energy transferred is power multiplied by time. Just a reminder. Units of energy now, this box at the top. So when you buy energy from your supplier, from your electricity supplier, you don't tend to buy numbers of electrons, which is good because there's quite a lot of them flowing, but also every electron that enters your house leaves the house. So what you buy is the energy that's transferred by the current into your house. And we don't buy that energy in terms of joules. We don't say it's sort of 10 pence per joule or 10 pence per 1,000 joules or anything like that. We use a different unit of energy. And it's a sensible unit of energy called the kilowatt hour. Now, let's understand kilowatt hours. 1 joule is equivalent to 1 watt second. Not 1 watt per second, 1 watt second. Look at this equation. If I put 1 joule in here, then I can make the equation balance with 1 watt of power being drawn for 1 second. They're together, P and T, which means we multiply them together. So it's not watts per second, which would mean watts divided by seconds. It's watt seconds. 1 joule is 1 watt second. But what if, instead of using seconds as the unit of time, I used hours? And what if, instead of using watts as the unit of power, I used kilowatts? Well, then I would have kilowatt hours as my unit of energy, not joules, but it's fine. So 1 kilowatt hour is the same as 1,000 watt hours. Okay, well, there are 3,600 seconds in an hour, so 1 hour is 3,600 seconds, so 1,000 watt hours is 3,600,000, so 3,600,000 watt seconds. And a watt second is, by definition, a joule. So 1 kilowatt hour is 3,600,000 joules. It's just another unit of energy. And at the moment it's, I remember back when it was about 20p, I remember when it was about 15p per kilowatt hour. So my kettle, it's, my iron, sorry, is 2,000 watts. So that's 2 kilowatts. If I use it for half an hour, then I have used 1 kilowatt hour of energy. So at 15 pence per kilowatt hour, it would cost me 15 pence to do half an hour of ironing. Unfortunately, it's now closer to 50p. It might even be more than 50p per kilowatt hour. So what used to cost me 15 pence in energy to iron my clothes would now cost me 50p, not 15p, to iron my clothes. That's quite a lot. How much does it cost to charge my toothbrush? Well, it's 1.2 watts. But it's on 24/7, isn't it? It's on 24/7. So 1.2 watts multiplied by, let's divide it by 1,000 to get it in kilowatts, and multiply it by 24 hours is 0.0288 kilowatt hours. At 50 pence per kilowatt hour, that's costing me 0.01 pence, 0.0144 pence per day. Across the year, that's costing me 5. Hang on, let's just check that maths. 1.2 divided by 1,000, multiplied by multiplied by 24 hours in a day, multiplied by 365 days. Right, so 0.5. So it's going to put me in pounds. My apology. I got my unit wrong because I forgot I was working in pounds. Don't make that mistake. It costs me £5.26 to leave my toothbrush charger on all year round at the moment. £5.26. I know. It's not a lot. It's not a lot. £5.26. But it used to cost me, let's just work out how much it used to cost me. £1.58. Now it costs me over a fiver. Politics. Anyway, so that's how you can make use of these numbers and understand what's going on. That's the end of this video. If you found that helpful, then do consider our weekly tuition sessions. They are interactive and live, unlike this, which is just a video. They're interactive and live and involve a lot of questioning and answering and stuff like that. Information's on physicswithkeith.com. Use the QR code there and go and enroll and register and stuff. Take care. I'll see you in the next video, which is all about materials science, solids, liquids and gases, materials, that sort of thing. Chapter 6. Take care.